How were they? How were those questions I gave you? Good or bad?
Me?
The ones I gave you, good or bad? From 1 to 10. 5.5, 5, 6, yeah, okay. Right. Yes, which is good news, I suppose. Maybe. Okay.
That's why I have a question.
Right, okay. What's the first question? I don't have it here.
There's only 2 questions, right?
Was there only 2?
Yeah.
That's too kind. Thank you for clearing that up. We wouldn't want to think I'm too kind. Okay. Oh, you're right. There's only 2 questions. I was too kind. Yeah. So the first one is you have a steam engine and it's burning coal, and the coal releases 10 kilojoules of heat during the first second. Oh, come on. It's going to be one of those days. Okay. Right. So I'll try and draw my train. Here's my train. I can draw a better train than that. Everything okay? The train? That's a train. Look at this beautiful train. What you talking about is it a train? Of course it's a train. And we'll make it Thomas as well. Why not?
I will show you the picture of what that is.
Oh yes, you should, yeah. Right, so Thomas the train now has his heat energy here, and we're looking at 1 second.
Oh,
Did you show Sophie?
Yes.
Yes. Did I what?
You too, Dennis.
No, Connell gave it to Dennis. Yeah. Okay, so the Q, what's the Q? The energy from the heat. Is it 10 kilojoules? Okay. And what's our formula that we have? The heat energy equals the work done plus the change in the internal energy. Wasn't that it?
Yeah.
Yeah. Now, oh yeah, so this is what we want, isn't it? So we can say the increase in internal energy is equal to Q minus W. Now, do we know the Q? Yes. But do we know the W? Do we?
No.
No. But we have a formula for W. What's that? Force multiplied by distance. Remember this one? Yes? Now, do we have force? No. But what's the formula for force? A. Do we have M? We do, don't we? 10,000. Do we have D? Oh no, wait, hang on. We know the V. Ah, that's better. Do you remember there was another formula for work? You could divide by, well, remember power. Power was work over time. But there was another formula for power. Does anyone remember it? It was kind of like the trick formula. F multiply V? Do you remember this one? No. Okay, better quickly show you. Power is work over time. Work is force by distance. But what is distance divided by time? Velocity. That's power. Power is work over time. But if I'm looking at 1 second, what's the T here? The T is 1. So the work is just FV. So if the T is 1, then the work is just FV. So this would be 10,000 minus F. Do we know? Do we know? No, we have to calculate it. Alright, so that's MAV.
Is W equal FV? But you say
For 1 second.
powers.
Yeah. Just be careful. I'm saying work equals FD and power equals work over time. But if the time is 1, it's the same then. Okay. The M is... I lost it. What was my M? What was my M? 10,000.
10,000.
And what's my V? 1. Okay. So what is my A? We have to get the A. We can use UVATS to get the A. Let's stick it here. UVATS. The T is 1. The V is 1. The U is 0. Well, you can guess what the A is. What do you think the A is? 1. Because you can remember, you can say V equals U plus AT. The U is 0. So V over T equals A. So V over T is A. So the A is 1. Wait, those numbers are bad. Change this to 20,000 in the question. And the answer is 10 kilojoules. I don't want the answer to be 0. That's very bad. That one was a bit difficult, I know. Did anyone get an answer? Oh no, well, if you use the 10 kilojoules, what answer did you get?
You get 0.
No, did you get 0? So what did you get?
Different. Very different.
Totally different, that's okay. This question is not going to be on the exam, I don't think.
It's too hard.
Not because it's too hard, but just because the syllabus isn't clear about what type of problems you need for this topic, and there hasn't been any question like this in the past. So I don't think you'll get one in like this in the exam. Okay, next now. So it's exactly the same question, except this time I don't give you numbers. I just say Q, W, and delta U. What's the efficiency? Okay, so if you look at our Dennis the train, there's Q from the engine, and this makes the train go forward, but then there's also internal energy. The train is a little bit warmer. Can you imagine that? That if you feel the train, it feels warm. This is the internal energy. Yeah? Yes? Do you want the train to feel warm?
No.
No, why not?
A waste of energy.
It's the waste of energy. You only care about which force here. Sorry, which energy do you care about? The work. And where does the work come from?
Q.
The Q. Yeah? So efficiency is, do you remember, it's power out over power in multiplied by 100. So what is the power out here? Or it doesn't have to be power, it could be energy out over energy in times 100. So what is the energy out? What do you get out? What energy comes out of the train that you want?
kinetic energy, right?
True, which is what letter here?
Or
Yeah. And what goes
Q.
what goes in?
Q.
Q. This is the energy that goes in from the coal, and then this is the energy that comes out. But this is the one you want, and you don't want this one. This is wasted. This is a waste. You don't care about this one. You want this one. Both of these come from the coal here. Now what does Q equal though? Q is the same as W plus delta U. And that's it. So, like this. Now please note, do you remember the second law we did last time? What does the second law say? No, not Newton's second law. The thermodynamics second law. Thermodynamics second law says that the heat cannot travel from the cold to the hot. Another way to say it can be written in different forms. Another way to say the second law is that delta U must be bigger than 0. This is another version of it. In fact, before, no, listen, just listen please 1 moment. Do you remember Newton's second law? There's 2 ways to say it. You can say F equals ma, or you can say F equals delta P over delta T. There's 2 ways to say it. Just like with Newton, there are different ways to say this law. So one way we could say it is that the energy cannot go from the cold to the hot. Okay? So you can write that down. But another way to say it is like this, that delta U must be positive. That's just another way to say it. Now let's go back to my question and see what that means. If this number here must be positive, what can we say about this? True. But something else more important. If this must be positive and can't be 0, is it possible to get 100%? No, because this here is always bigger than this. So another way to say it is that the efficiency is always less than and never equal to 100%. So these are different ways to say it. And there's actually another way to say it, but that's to do with chemistry, so I won't say that one. But maybe Lorraine will do it with you. You can tell me this. Have you ever heard of this word in chemistry? Entropy. No. It's letter S. You'll do it in chemistry. And the rule is entropy, its change is always positive. Anyways, that one's for chemistry. So this one is chemistry, physics, physics, physics. This is the second law. So, just to finish this topic, please notice we're saying that it's a law that you cannot get 100%, that 100% is impossible.
But you can at 0 Celsius.
Yeah, but I mean, to make 0 Kelvin, you're going to have to use a lot of energy. No, it's impossible. Yes. If you find a way to make it not impossible, then you shall become very famous. Very famous, but it's very impossible. Okay, can I close this now? Okay.